Okay, so Friday we took our test. I'll have those graded and back to you this next Friday. So now we're going to start Unit 2. Unit 2 starts our discussion on measurement. So along with measurement, we're going to end up doing a little bit of basic geometry and some other calculations along with it. But today we have to tackle not one of my favorite topics, but it's a very important topic to discuss in measurement. And that is errors in measurement. All measurement is approximate. In other words, all measurements are rounded. And what do I mean by rounded? I mean they're going to a nearest unit on a measuring device. So let's look at length, just because that's the easiest one to illustrate. And let's just go to the standard ruler. And we're going to mark off our ruler in a unit we're familiar with. We're going to mark it off in inches. So if I put a line on here, now of course we all know how to measure with any ruler or tape measure. You start at a zero end at one end of the object, and you see where the other end stops is where you read your measurement. So we line up our zero end here. And to measure that blue bar, we would look at this and say that is closest to the 2-inch mark. Now you might say, well, it's about halfway in between. Can't we say 2.5 inches? And the answer is no. We cannot say 2.5 inches because this measuring device is not capable of measuring to the 1/2 inch. It's only capable of going to the nearest inch. So we have to make sure that we report it honestly to indicate what our device is capable of. Now if I put this green bar in here, that would also be recorded as 2 inches. Now the green bar and the blue bar are not the same length, but this measuring device is not capable of distinguishing between them. We call that precision. The precision of a measuring device is it's the ability to distinguish between similar objects. So this measuring device cannot tell the difference between the blue bar and the green bar. It is not precise enough to tell the difference between those objects. Well, how do we make it more precise? Well, the easy way is just go ahead and cut each unit in half. So it's our 1/2 inch, 1.5 inch, 2.5 inch. Well, I didn't quite get that in the middle. Let me try that again. Right there, 2.5 inches. Still though, both of those, the blue and the green bar, would be closest to the 2.5. So again, we're not quite precise enough to tell the difference between those. So to make it more precise, we'll cut them in half again. We'll go to quarters. And now I would say the green bar is closer to the 2 1/4, while the blue bar is closer to the 2.5. So finally, this measuring device is precise enough to tell the difference. And that is called the degree of precision of the measuring device. And the degree of precision is simply equal to the smallest division on the device. So for this ruler, the smallest division is 1/4 inch. So the degree of precision is 1/4 inch. It is capable of measuring to the nearest 1/4 inch. However, when we look at this, the blue bar is not exactly at 2.5 inches, is it? In fact, if it had been anywhere from here to here, we would have counted it. We would have had to reported it as 2.5 inches. That's what we mean when we say all measurement is rounded or all measurement is approximate. It has to be reported to the nearest division on the ruler. Because it is rounded or approximate, there is a built-in error in any measurement we do. And you can see here that that error is half of the distance to the next division of the ruler. So the possible error in a measuring device is 1/2 of the degree of precision. So for this ruler, the degree of precision was 1/4. So 1/2 of 1/4 is an 1/8 inch. So the possible error in this measuring device is plus or minus an 1/8 inch. So what that means is anything we report, any measurement we could report, the actual object could be an 1/8 inch smaller to an 1/8 inch larger. Here, the blue line was reported as 2.5 inches. Well, it could have been an 1/8 inch smaller or an 1/8 inch larger and still reported as 2.5 inches. So what that means is any measurement we report has that error in it. So now when you guys are working out in the shop, does Josiah have you measuring to the nearest 1/8 inch or the nearest 16th? 16th? Okay. This might take a minute to draw out, but I believe I got 16 spaces there. So here's a ruler marked out to the nearest 16th of an inch. Most of your tape measures only go to the nearest 16th of an inch. Actually, usually the first 2 or 3 inches might go to the 32nd or 64th, and then after that, they only go to the nearest 16th of an inch. First of all, you can tell by counting between labeled divisions how many spaces there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 spaces between 0 and 1 inch here. So that means each space is a 16th of an inch. So that means the degree of precision for this measuring device is a 16th of an inch. Now, are your tape measures capable of measuring smaller than a 16th, and that's just as small as you go, or do they only go down to the 16th of an inch? They just go to a 16th. So the degree of precision on your tape measures is a 16th of an inch. So that means everything you measure has a possible error. How do we find the possible error in your measurements, given that you're going to a degree of precision of a 16th of an inch? Well, it's 1/2 times your degree of precision. What's 1/2 times 1/16? 1 times 1 is 1. What's 2 times 16? 32. So everything you measure with your tape measure is plus or minus 1/32 of an inch. So what that means is, let's say you measure an object and your measurement is given as 14 3/4 inches. Because of the degree of precision of your ruler and this built-in possible error of plus or minus a 32nd, that measurement of 14 3/4 is actually implying a range. When you measure something and report it as 14 3/4 of an inch, what you're saying is it is less than a 32nd smaller. So 1/32 smaller, well, 14 3/4. 3/4 would be 20, oops, I don't know where the 34 came from. Would be 24 32nds. Minus 1/32 would be 14 23 32nds of an inch. 2, that 14 3/4, well, I'm just going to write it as 14 24 32nds plus a 32nd. So that's 14 25 32nds. So on your tape measures, when you report a measurement of 14 3/4 inches, what you're actually saying is the object you measured was somewhere between 14 23 32nds and 14 25 32nds. It was just closest to the 14 3/4. So that's what you reported. And you have to keep, now for you guys in construction, it's not such a big deal. But if you go on to the next level of design and engineering, keeping in mind that any measurement that is reported is actually a range of actual possible measurements is very important in doing our calculations. And when we do a measurement with standard measure, fractional standard measurement, which is what we've been using here for the last 10 minutes or so, we have to have that knowledge of our measuring device. So either we have to have a picture of the measuring device like this, so on this measuring device, what is the degree of precision? What's the smallest unit on this measuring device here? Careful. There's between 1 inch and 2 inch, there is only 8 spaces. So each division is 1/8 of an inch. So that means the possible error is half of that. What is 1/2 times 1/8? A 16th. So that means the possible error in this measurement is plus or minus a 16th of an inch. So a measurement that is reported at, let's do 7 1/4 inches. Again, is implying that range of 7 1/4 minus a 16th to 7 1/4 plus a 16th. Well, I'm going to change this. 7 1/4 is 4/16 minus a 16th. That's 7 3/16 inches. To 7 1/4, I'll write it as 7 4/16 again, plus a 16th is 7 5/16 inches. So we can either have the picture of the measuring device like we did here, use that to define the degree of precision and then the possible error, so that we can understand that that 7 1/4 inch measurement is really saying that the object is somewhere between 7 3/16 and 7 5/16. Or we can be given a measurement of, let's say, 3 5/8 inches on a device with a smallest division of 1/8 inch. If the smallest division is 1/8 inch, that means the degree of precision is the degree of precision is just the smallest division. So the degree of precision is just 1/8 inch. So that means the possible error is plus or minus a 16th again. So 3 5/8 is 3 10/16. So minus a 16th would be 3 9/16 plus a 16th would be 3 11/16. Perfect. So we know that that reported measurement of 3 5/8 inches is really saying, excuse me, that object is somewhere between 3 9/16 and 3 11/16 inches. If we use decimal measurement, the degree of precision is implied in the way we write the measurement. For example, if I give you 23 inches or 23.0 inches, is there a difference between those two measurements? No. Mathematically, 23 and 23.0 are the same values. But when we're dealing with measurement, there is an implication to that extra decimal place at the end. If I report that measurement as 23 inches, what that is implying is that I have a measuring device that is capable of measuring to the nearest inch, and whatever I measured was closest to 23 inches. The degree of precision of a decimal measurement is just the place value of the last digit. So for 23 inches, the degree of precision is simply 1 inch. So that means the possible error is plus or minus half of 1 inch, or half an inch, or 0.5 inches. Which means that implied range, or that possible range, is from 23 minus half an inch, so that's 22.5 inches, to 23 plus a half an inch, 23.5 inches. So when we report that as simply 23 inches, it is saying it's anywhere from 22.5 to 23.5 inches. Over here, however, when we report that as 23.0 inches, what that is implying is it's implying that our measuring device is capable of measuring to the 10th of an inch because we have that last digit in the 10th of an inch. It's implying a degree of precision of 0.1 inches, or 10th of an inch. So what it's saying is, when we measured it, we were capable of going to a 10th of an inch, but it was still closer to exactly the 23.0 inches. So the possible error is now half of that, or 0.05 inches, plus or minus 0.05 inches. So that means that that implied range is from 23.0 minus 0.05, which is 22.95 inches, to 23.0 plus 0.05, so 23.05 inches. So it's tempting to just add that decimal place at the end. 23.0 numerically is the same value as 23. But if we add that decimal point, that 0.0 onto the end, it is implying that extra piece of information, that extra step smaller in our degree of precision. So if I report 4.38, and I know you guys work primarily with standard units, but the metric system is coming. I don't know when, but it'll be here before your guys' life is over. 4.38 centimeters. That is implying then a degree of precision What is the place value of that last digit? 100th. So that's 0.01 centimeters is the degree of precision. So the possible error of that measurement, what's 1/2 or 0.5 times 0.01? Well, it's 0.005 centimeters. So our error is plus or minus 0.005 centimeters. So then the range, well, 4.38 minus 0.005. If I add that 0 on the end and I do my borrowing, that's 4.375 centimeters. To 4.38 plus 0.005. So 4.385 centimeters. Okay. The next item is one of those items that will appear on a quiz and it will appear on a test, but it's one of those items that we will work through together. I don't expect you to be able to do it on your own, but it is something that you need to be familiar with, because if you're looking at a textbook, looking through solutions in a textbook, this is how most math and science textbooks round their answers, is according to something called significant digits. Anybody in the group had either chemistry or physics? A couple of you? Okay, so if you've dealt with physics or chemistry, you've probably heard significant digits, and you probably didn't care much for them. And yep, sig digs. Your significant digits deal with exactly what we have been discussing, but they kind of do it in a hidden way with the terms of significant digits. But the reason for them is exactly what we have been discussing. It keeps track of the possible errors in our measurement. Now, like I said, it's not important that you guys be able to calculate with significant digits. So when we see these problems on a quiz or a test, we will work through them as a group, and then you can do the other problems on your own. But I do want to show you what they are and get you guys some sort of a basic understanding of how they work. So in significant digits are any digit that is important or relevant to a measurement. So I put relevant in there instead of the word important, because there are a lot of digits that are very important but not significant. So when I ask for what is a significant digit, what digits are significant? Well, the first one is any digit that's not a 0. So if I have 53, that is 2 significant digits because neither of those digits are zeros. They're both non-zero. Zeros can be significant if they meet one of 3 conditions. The first one is if they're between other significant digits. Well, what does that mean? Well, if I have 208 inches, the 2 is significant and the 8 is significant because they're not zeros. Well, this 0 is between them, so since it's between other significant digits, it's also significant. So that has 3 significant digits. If I have 6,040 inches, now the 6 is significant because it's not a 0. The 4 is significant because it's not a 0. This 0 is between significant digits. It is significant. However, this 0 is not significant. It's not between other significant digits. So that 6,040 only has 3 significant digits. Another way a 0 can be significant is if it is indicated as significant. To indicate it as significant, we either have to put a line above it or below it. So 6,040, I can either put a line above that 0 or below the 0, depending on what textbook you're using. Now that 0 is indicated as significant. So the 6 and the 4 are significant. That 0, of course, is between them. So this now has 4 significant digits instead of 3 because that 0 was indicated. This third possibility for the zeros is the one that people find the most difficult to remember. And that is otherwise unnecessary. What that means is if there's no other reason or no other need for that number to be there. Like if I have the number 7,000 inches, those zeros are necessary because if I take them out, it changes the whole meaning of that number. 7 is a very different number than 7,000. Those zeros are not significant because they are necessary. They are needed there to give value to the 7. This only has one significant digit. The 7 would be the only significant digit. So when would they be unnecessary? Well, otherwise unnecessary, there's only really one situation where that happens. It has to meet both of these qualifications. It has to be after the decimal and at the end of a number. So what does that mean? Well, let's do 30 inches. The 3 is significant because it's not a 0. That 0 is not significant. That only has one significant digit. But if I write it as 30.0 inches, the only reason that 0 is totally unnecessary. It's like that example we did a few minutes ago. 30 and 30.0 are mathematically equivalent. This 0 is not mathematically necessary. So the only reason for it to be there is if it's part of the measurement, which means it is significant. So since the 3 is significant and that 0 is significant, that 0 is between them makes that significant. So this has 3 significant digits. So what significant digits really are discussing is digits that are part of the measurement and not just part of the mathematics, or not just part of the placeholders. So the biggest, only confusion really is whether a 0 is significant or not. So we might have a problem like this. 0.008040 inches. So here, the 8 and the 4 are definitely significant because they're not zeros. These zeros up here, however, are not significant because they're needed for the number. They are just placeholders. This 0, how about this one? Is that one significant? Yes or no? Yeah. Perfect, because it's between the 8 and the 4. So yes, that is significant. The tricky one, of course, is this last one. It's at the end of the number and it's after the decimal point. So that means yes. Remember, if it meets both of those qualifications, after the decimal and at the end. So that is 4 significant digits in that number. Now, like I said, I am not going to expect you guys to be able to look at a number and count up significant digits on your own. That is something that we will work on together. In engineering or in pure science like physics and chemistry, it is important for your error analysis. For construction, we're not really into precision measurement that much. But if any of you were to go on to a machining program, which this math course does transfer into, in machining, precision measurement is a lot more important. Significant digits does become a big deal in machining and mechanical design. So the significant digits then bring us to the ability to classify a number in terms of its precision and its accuracy. So the precision of a number, just like with our decimal measurement, is simply the place value of the last significant digit. So we saw if I have 23.0 inches, this 0 is significant because it's after the decimal and at the end of the number. So the precision of this number, well, what's the place value of that digit? The tenths. So the precision of this measurement, 23.0, is it's down to the tenth of an inch. If I have 40 inches, however, the 4 is significant. Is that 0 significant? No, it's not. The way it's written, at least it isn't. The precision of that is just to the nearest 10 inches. What if we measured something and it came out to be 40 inches? We're measuring to the nearest inch, but it came out to be nearest to 40 inches. How would we have to indicate that? Well, we would put a line either above or below that 0, indicating we really did measure to the nearest inch. So if that indicator there, then that is a significant 0. And this is now precise to the nearest 1 inch instead of just to the nearest 10 inches. So it is something, if you are reporting a measurement, it is something to consider if it comes out to be exactly 40 or 60 or whatever, to do that indicator that you really did measure to the nearest inch. Accuracy is the number of significant digits. So if I report a measurement of 42.3 inches, the accuracy of that number is it is accurate to 1, 2, 3 significant digits. So if I report a measurement is 2.067 inches, what is the accuracy of that number? How many significant digits does it have? 4, there you go. I heard the confidence slowly creeping into your voice there. 4 significant digits. So it is accurate to 4 significant digits. Again, a measurement like 40 inches, well, 4 is the only significant digit. That is only accurate to one significant digit. But if you actually did measure to the nearest inch and reported it with an indicator under the 0, well, then it's now accurate to 2 significant digits because the 0 becomes significant. Why are precision and accuracy important? Well, because that's how we round our measurements when we calculate. Now again, for this class, I am not going to expect you to round your measurements to significant digits. But if you're looking in an instruction manual, any sort of engineering document is going to have calculated measurements will be rounded to significant digits. So at the very least, I want you to be able to be familiar with it so you understand when an engineer or an architect does round a measurement, why they're rounding it the way they are. So when we round measurements, when we add or subtract, we preserve precision. What that means is we're concerned about the degree of precision or the place value of the digits when we add or subtract. If I have 43.7 inches plus 6.58 inches, if I add those measurements together, I get 50.28 inches. Well, I have to round that to the appropriate place value. And to find that place value, I look at my measurements, the degree, and I look at the precision of each measurement. What is the precision of this first measurement here? Remember, precision is place value. So what's the place value of that last digit? That's the 10th. So that's precise to the nearest 10th of an inch. How about this number? What's its precision? Nearest 100th of an inch. Which one is less precise? The 10th of an inch is less precise. So what that means is I have to round my measurement to the nearest 10th of an inch, the less precise input of our calculation. So the 10th of an inch is right there. If I round it to the nearest 10th, does this round up or down? Bless you. Yeah, that 8 means we round up to 50.3 inches. Now you might be wondering, well, how is rounding that measurement make it more accurate or more precise? Well, it doesn't. We lost information by rounding that measurement. But the reason we had to round the measurement is because this measurement is only precise to the nearest 10th. It has an error of plus or minus 0.05 of an inch. What we rounded off here was less than what that error was. So we had to trim this back to the nearest 10th of an inch because some of our inputs are only have that error of plus or minus 0.05. So we have to round our answer so that it also has an error of plus or minus 0.05. We're accurately reporting what the possible error of our measurement is. Yeah, I know this is an enthralling topic. Bear with me. We'll do it today and then we'll get past it. So anyway, if I look at subtraction, let's do 3,240 inches minus 3.875 inches. If I subtract these, 3,240 minus 3.875, I get 3,236.8 0.125 inches. But when we add or subtract, we preserve precision. What is the precision of this number right here? Well, the last significant digit is the 4. That 0 is not indicated, and it's not after the decimal point, so it cannot be significant. Remember, it either has to be indicated, it has to be between other digits, or it has to be after the decimal point and at the end of the number. That's at the end of the number, but it's not after the decimal point. So what's the place value of the 4? That's the tens. So that measurement has a precision of 10 inches. It's to the nearest 10 inches. How about this measurement here? What's its precision? That's tenths, hundredths, thousandths of an inch. Well, it's pretty obvious here that the less precise one is the nearest 10, which means I have to round my answer to the nearest 10. So there's my tens digit. What does it round to? This one here, to the nearest 10. There's the tens digit. $3,240. You got it. Well, if I look at that, that's exactly what I started with, was 3,240. We subtracted 3.875 inches, and it didn't change our number at all. The reason why? Well, because the error in this measurement here is plus or minus 5 inches. What we were trying to subtract from it was smaller than the error of the measurement. Now, this is an exaggerated example, but the point of it is you should not try to add or subtract numbers that are on severely different, what we call order of magnitudes. If you have something that is measured as 8.5 inches and you want to add something that is measured as 0.038 inches, it really can't be done because this measurement is so small compared to this one that the degree of precision of this one is only 1/10 of an inch. So that the error is plus or minus 0.05 of an inch. Well, that's bigger than this measurement. So if the error in one measurement is bigger than the other measurement, you should not be combining those two measurements. Again, I don't expect you guys to do this on your own, but I want you to be familiar with the process. When we do these together, hopefully you guys will be able to, with a little prodding, work through them as a group without me having to say a whole lot about them. When we multiply or divide, we are worried about accuracy. Remember, accuracy is the number of significant digits in a measurement. So if I have 42 inches times 4.75 inches. Well, we multiply that out. We get 199.5. Of course, inches times inches is square inches. Figuring out where we have to round that answer now, we look at accuracy. Remember, accuracy is the number of significant digits. How many significant digits are there in this measurement here, the 42 inches? 2 significant digits. Good. How about this one here, 4.75 inches? 3 significant digits. So which one is less accurate? Well, 2, right? So what that means is we have to round our answer to 2 significant digits. So we start at the beginning, we go 1, 2, we're going to have to round it right there. Well, this one's actually a great example because it shows us one of the quirky things that can happen. That 9 tells us we have to round up, Well, that rounds up to 200 square inches. However, the tens digit here is significant. So we have to make sure that we indicate that 0 with a line either below it or above it, that 0 is significant. That this is measured to the nearest 10 inches. It just happened to be closest to 200. Now, with that all said, like I explained, I'm not going to force you guys to do a lot of calculations to significant digits. We are going to practice some, but if you're not an expert at it, I'll leave that to your physics class to drill that into you. It's not that important in construction. Like I said, it's important to us on the engineering and the architectural side of it, not on the actual building side of things. The part that is a little bit more important for us is dealing with those errors. So we saw that there is a possible error built into every measurement. Well, let's look at real errors. So the first type of real error is something called an absolute error. And an absolute error is simply a difference between an actual length or actual size and the measured size. And I put these lines around it. Does anybody know what those lines mean? They mean what? Absolute value, good. And what it really means is it doesn't matter which number is larger, the actual size or the measured size. All I'm looking for is the difference between them. So whether that turns out, when I subtract, whether it turns out to be positive or negative, I want the positive difference between them. So if I have an object that has an actual size of 4 3/32 of an inch, and it gets measured as 4 1/16 of an inch, the absolute error is just the difference in those measurements. So the bigger one here is the 4 3/32. I'll subtract the 4 1/16. 1/16, of course, is 2/32. So the difference there is 1/32 of an inch. That is the absolute error between those two measurements. Well, absolute error doesn't always tell the whole story. We often need something called a relative error. And along with the relative error, we have percent error. Some textbooks just treat them as the same thing, just two different ways of expressing it. Other textbooks use relative error and percent error differently. Really, they are the same thing, just one is expressed as a percent, the other is expressed as a rate. So the relative error is the absolute error divided by the actual value. So for this example here, the absolute error is 1/32 of an inch divided by the actual value of 4 3/32 of an inch, which will divide out to 0.00763. That is my relative error. The percent error then is just to convert that number to a percent. From a rate to a percent, you just move the decimal point over 2 spots. That's a 0.73% error. as a percent error. Relatively small. So what is too large of an error? Well, that's one of the reasons why we use the relative error rather than the absolute error, because the error being too big or too small really does depend on how big the object is. For example, let's look at object 1, or we'll call it object A, and object B. So object A has an actual size of 2 3/8 inches and is measured as 2 1/4 inch. Object B has an actual size of 18 7/8 inches and is measured as 18 3/4 inches. Well, the absolute error for object A, well, 2 3/8 minus 2 1/4, well, that's just 1/8 of an inch. For object B, well, 18 7/8 minus 18 3/4, that's again 1/8 of an inch. They both have the same absolute error, but the story really is completed with the relative error. And the percent error. So for object A, that's 1/8 of an inch divided by 2 3/8 inches, which gives us 0.0526, or as a percent, 5.26%. 5% error is too large. That's more than what we want to deal with. But for object B, we have an absolute error of 1/8 of an inch divided by an actual measurement of 18 7/8. Gives us 0.0066. Or as a percent, moving that decimal over, it's 0.66%. Well, that's less than 1% error. That's fine. So the relative error of 1/8 of an inch, or sorry, the absolute error of 1/8 of an inch in one case is too large and in the other case is okay because of the size of the object. Well, where this ties in with where we started today is, well, how do we know the absolute error? If we know the actual size, there's no reason to measure the object. We're taking the measurement in order to estimate the actual size. So we don't know what the actual size is, so there's no specific way to calculate the absolute error. So what we do in practice, we use for the absolute error we use the error, or the possible error, of the measuring device. So if we have a measuring device that's only capable of going to a 1/4 inch, so if the degree of precision, or the smallest division on the ruler, is a 1/4 inch, that would mean the error is 1/8 of an inch, or plus or minus 1/8 of an inch. Well, if what we're measuring is only 2 3/8 inches long, That's too big of an error. We need a more precise measuring device for that. If what we're measuring is 18 7/8 inches long, measuring it with a ruler that's only capable of going to the 1/4 inch is just fine. That's only 0.6%. So that when it all comes together is knowing whether our measuring device is adequate depends on the size of what we're measuring. If we're measuring something small, we need to have a much smaller degree of precision to get a suitable measurement. If we're measuring something large, in this case, only if it's 18.5 inches long or 18 7/8 inches long, we only needed to go to the nearest 1/4 inch and we were just fine with our errors. Well, I see I'm about ready to put all of you guys to sleep, so let's give you something to work on here for our last 14 minutes or so. Make sure I have the correct pages out of here. 203 or 225? Let's check. That's definitely not it. Okay, so we have a few pages to put together here. So these are all in the big book. Starting on page 266 and going through page 270 is exercise 7-4, 7-5, 7-6, 7-7, and 7-8. So these are dealing with degree of precision, possible error, and some significant digits. Like I said, work through what you can, be familiar with them, and we will, any graded assignment, we will do them together as a group. Okay, we have about 12 minutes left. I'll let you guys work for 12 minutes, and then we'll get you out of here.